Alright, in this video we're going to talk about angular speed and linear speed, right? So it's two different ways to talk about the rate at which something is changing when that something is rotating around, right? So you can think of it as like the fans of a blade spinning around, or like the propellers of a motor in a boat or something like that. Anything that's rotating has two different speeds. It has the angular speed, which is the rate that the angle is changing, and it has a linear speed, which is the rate, if you're talking about like an overhead fan spinning around, like if you take a point on the end of the fan, at what rate is that distance changing? All right, so we'll talk about each of them separately. We'll look at the formulas for each, and then I'll erase all this in a minute and put up an example where we find angular and linear speeds. All right, so the angular speed is the rate at which the central angle theta is changing. Right, so when something's spinning around, it's rotating at a certain speed. Right, the rate that angle is changing as it spins around is what we call the angular speed. So to find the angular speed, it's the number of radians the angle is changing divided by the time elapsed. Very important here, number of radians, right, not degrees. So if we are trying to find angular speed, and also for linear speed, our angles have to be measured in radians in order for these formulas to work out. Which, if you watch the video that I did on arc length, the length of the arc of a circle, in that formula as well, the theta has to be in radians. The angle has to be measured in radians. Right, so to get our angular speed, it's the number of radians the angle changes divided by the time it takes for it to go that far. So, if it takes, if one full rotation is 2 pi radians, and that one rotation takes 1 whole minute, well, then your angular speed is 2 pi radians per minute, right? That's how many radians it went in 1 single minute. Now, most of the problems obviously are not going to be that simple. I just chose really easy numbers there. But our formula, right? This letter that looks like a W is actually the Greek letter omega, which I wrote down here, right? So omega is what we use for our angular speed. Omega is equal to theta, the measure of the angle that this thing is moving, divided by t, time, right? So again, if it goes 2 pi radians, 1 full circle, and it takes 1 whole minute to do that, well, then the angular speed is 2 pi radians per minute, right? So your units on your angular speed is going to be in radians per minute. Not always minute. It could be radians per second. It could be radians per whatever unit of time. So it's radians per some unit of time. All right, it doesn't always have to be minutes. That's just the example that I used. All right, so that's how. But the key thing is that the measure of the angle always has to be in radians. All right, so that's what we call the angular speed, right? The rate at which our angle is changing as time goes by, radians per some unit of time. All right, linear speed refers to, again, if I have a fan blade spinning around, the tip of that blade is covering a certain amount of distance over time. So the distance that it travels divided by time, that's its linear speed. Right, actual distance traveled, not the angle traveled, right? So linear speed is the rate at which the distance traveled is changing, right? So it's the distance traveled divided by the time elapsed, right? So if my fan blade spins around a total of 10 feet in a minute, then its linear speed is 10 feet per minute, right? So depending on the actual distance that it travels as it goes around the circle, measuring the actual length of that, not just the angle in the middle and how that's changing. Right? So that's the difference between the linear speed and the angular speed. So it's distance traveled divided by time elapsed. So v, we use the letter v for linear speed, which corresponds to velocity. V is equal to s over t, where s is the distance traveled, which is the arc length. Right? If something's traveling around the circle, the distance that it travels is an arc length. Right? Remember, arc is some portion of the circumference of the circle. Right, so it's the arc length divided by time, and the arc length, again, I just did a video on arc length. The formula for arc length is S equals R times theta. The radius of the circle times theta, the angle that's covered in this time period. And once again, for this formula, just like for this one, theta has to be in radians. Right, so my units when I'm doing the linear speed is going to be feet per minute or inches per second or meters per hour, some length divided by some unit of time. Right, so that's what it's going to look like for linear speed. All right, so a lot of times when we're doing linear speed, the first thing we have to do is figure out what s is. We have to calculate the arc length using this formula, and then plug that number into this in order to get our actual linear speed. Right, so sometimes for the linear speed, it's a 2-step problem in order to figure that out. All right, so those are the definitions of angular and linear speed, the formulas that we're going to use to figure those out. I'm going to pause the recording now and erase all this and put up an example, and then we'll calculate these two things for this particular example. All right, so the example we're going to look at here, we have a boy who rotates a stone in a 3-foot-long sling at the rate of 15 revolutions every 10 seconds. And we're asked to find the angular and linear speed of the stone. All right, so here's the boy. He's got a sling. He's whipping it around. He's got this stone in it. So the radius of the circle, like as he spins it around, he's making a circle. The stone is traveling in a circle, and the radius of that circle is 3 feet, right? Because the length of the sling is 3 feet. As he spins it around, if his hand is like the center of the circle, that length of the sling, the 3 feet, would be the radius of the circle. All right, so I know my radius is going to be 3, and if I start with my angular speed, let's start with that one. So my angular speed, omega, is going to equal the angle traveled, theta, divided by time. Well, they don't give me the angle that this stone is moving. They tell me that it does 15 revolutions every 10 seconds. So if I do 15 revolutions, how many radians is that? Well, think about it. If a revolution means 1 full trip around the circle, right? So how many radians are in 1 full trip around a circle? That's 2 pi radians, right? So my theta, my angle, is going to be the 15 revolutions, right, times 2 pi radians per revolution, right? Every revolution is a full trip around, which measures 2 pi radians, right? That's the angle measure of a full circle is 2 pi. And the revolutions cancel out there, so I get 15 times 2 pi, so my theta is going to be 30 pi radians, right? So that's the angle measure that this kid is spinning this stone around every 10 seconds, right? So when I go back up here, my angular speed, omega, is equal to theta, which is 30 pi radians, per time, which is 10 seconds. Let me put the units here, right? So it's 30 pi radians for every 10 seconds, right? So just to kind of pause here and go back over how we found this, right? Excuse me, they didn't give us the angle, they just told us 15 revolutions. A revolution is a full trip around the circle. Each revolution is 2 pi radians, so I do 2 pi, and I'm doing that 15 times, right? So I do 2 pi times 15, that's where I get my angle measure of 30 pi, and he's going through that much of an angle every 10 seconds, right? Because that's how long it takes for him to do those 15 revolutions. All right, so 30 pi over 10 radians per second, and if I can divide 30 by 10, all right, that's going to give me 3, so this is going to be 3 pi radians per second. Right, so this stone is, the angular speed of this stone is 3 pi radians per second. Remember, 2 pi is a full circle, 1 pi is a half a circle. Right, so basically this thing is going 1.5 circles every second, right? And if you do that, if you do 1.5 circles every second, in 10 seconds, you're doing 15 revolutions, right? So that's what that 3 pi radians per second means. 3 pi is 1 full circle plus another half a circle. So for every second that goes by, this stone is going through 1.5 full revolutions, or 3 pi radians per second. All right, so that's the angular speed. All right, so that's our angular speed. Let's take a look at the linear speed. Right, the linear speed, which is v, is equal to s over t, where s is the arc length, the actual distance that we're traveling around the circumference of the circle in this particular period of time. Well, to get the arc length, s, the formula for that is s equals r times theta. Right, well, once again, my theta was 30 pi. Right, that's what we found out by doing the 15 times 2 pi. So my theta is 2 pi. My radius is the 3 feet. Right, notice we don't need to use the radius to find the angular speed. The angular speed is just the rate that the angle is changing. The length of the radius of the circle has nothing to do with how that angle is changing, right? So the radius doesn't come into play when I'm dealing with the angular speed, but with the linear speed, and if you think about this, if you have like a fan blade, the tip of the fan blade, the linear speed of that is faster than the linear speed of the inside of the fan blade, right? Because the inside of the fan blade has to go through a smaller circle, the outside of the fan blade has to go through a much bigger circle, but they do that in the same time, right? So the one on the outside, or the point on the outside of the fan blade, has to be moving faster than the point on the inside, right? Because it goes through a longer distance, a bigger circumference of a bigger circle, in the same time that that inner part of the fan blade moves through a smaller circle, right? So the linear speed does depend on the radius. It depends on how far you are from the center of the circle. The farther out you are from the center of the circle, the faster you're moving around, because you're going through a larger circle, a larger circumference, and you're moving at a faster rate because you're keeping the same pace as something that's closer to the center, and you're doing that at the same time, right? So the linear speed, that the bigger the radius is, the faster the linear speed is going to be. So S is equal to R times theta. My radius is 3, and my theta was, what was it again? 30 pi. So it's 3 times 30 pi, right? Which is going to equal 90 pi feet. Right? Remember, my arc length uses the same units of measurement as my radius does. So if my radius is measured in feet, my arc length is also measured in feet. Right? So what we're saying then is, in these 10 seconds that go by, right, my time period is 10 seconds, the stone is traveling through a distance of 90 pi feet. All right, so it's going 90 pi feet in every 10 seconds. Right, that's the actual linear distance that is traveling around the circumference of this circle at the end of this sling that this kid is whipping around here. Right, and the 90 over 10, once again, I can simplify that. That's going to give me 9. So it's going to be 9 pi feet per second. All right, that's going to be the linear speed of the stone as it goes around, as this kid's spinning it around. Right, so to get the angular speed, you first have to get the angle, theta. If they give you revolutions, you have to multiply each revolution times 2 pi. Remember, you have to do this in radians, not in degrees. So don't multiply 15 times 360 degrees. You multiply it by 2 pi radians to get the actual angle measure, and then that divided by whatever the time period it is that it takes to do that many revolutions, in this case was 10 seconds. Simplify that, that gives you your angular speed. For linear speed, we had to find the distance traveled, which is the arc length. So we had to use the arc length formula. And I did another video where I just explained this arc length formula and kind of where it comes from and how to use it. So if you haven't seen that video yet and this part was confusing to you, check out the video I did on arc length where I explained this part. So S is equal to R times theta, so it's my radius, times the same theta that I used up here, right? The same angle that I got from the 15 times the 2 pi, right? I use that in both of these formulas. I get that arc length, and then the arc length divided by the length of time. Simplify that. I've got my linear speed. All right, so that's angular speed and linear speed. That's it. Know those formulas. Know how to use them. That's about it.